All right. Welcome, everyone. My name is Pavan. I will be your moderator for the session. Just a quick reminder, we will do Q&A towards the end of the presentation. You may go ahead and ask your questions by clicking on the presenter tab on the right-hand side. And this way you can also engage with other attendees and ask questions, and then we will get to them a little bit later. And as of now, I just want to go ahead and welcome Simon with RedNote to the stage for the session. And he's going to be talking about leveraging Iceberg for AI BI workloads at RedNote. And with that, Simon, the floor is yours.
Okay, can you hear me, Sonny?
Loud and clear.
Oh, okay. Hello, everyone. This is Chao from RedNote, and you can call me Simon for alias. And today I'm glad to share how we are leveraging Apache Iceberg for both AI and BI workloads. And since I haven't practiced my English for a long time, so if you lost in my talk or the following QA session, please drop me an email. I will reply it in written English. So let's start. First, let me take a moment to introduce you about our company and our team. RedNote is a Chinese leading social media platform. Combines lifestyle sharing, community interaction, and online shopping. Some of you may heard of it when we absorbed a wave of TikTok refugees in January this year. People around the world sharing their life experience on this platform. And one of the hot topics is the cat tax. The Chinese netizen humorously informs the newcomers that the posting cat photos are a requirement to join the platform. I like the explanation. Once you post your cat, you can't do shame things, or you will lose your cat face. Okay, back to our team. We are the data infra team, helping to build the core offline data pipelines, and we are leveraging open source softwares for our daily job. For example, we are using Spark, Flink, and Ray for the computer scenario. We are using Clickhouse and StarRocks for the OLAP scenario, and Kafka, Iceberg, and Payment for the storage layer. Yeah. So here is today's agenda. Firstly, I will briefly introduce the technical background, including the whole picture of our data architecture and the overview of Iceberg adoption, followed by three main use cases which we benefit from Iceberg. The first case was streaming ingestion based on Flink and Iceberg. We got fresher data. And the second use case is about the OLAP scenario. We got perform fast queries based on the StarRocks Iceberg solution. And the last topic would be AI applications. We build a sample lake based on Iceberg to facilitate the offline future engineering. So let's move into the first part, background. Here is the brief picture of our data architecture. It's a typical Lambda architecture. The offline data pipeline consists of three layers. The stream layer backed by Kafka and Flink. The batch layer backed by Spark, Hive, and Iceberg. And the transformed data is loaded and merged into the OLAP warehouse backed by Clickhouse and StarRocks for the BI queries. And besides the BI workload, we have AI applications which can directly read the data lake results in the batch layer. Yeah, this is the whole picture. And as a summary, Iceberg is ubiquitous at RedNote. I give you some numbers. We have a total storage over 100 petabytes, and data increased more than 3 petabytes. And there are more than 1,000 active production tables, which are backed by catalog and S3 file and Parquet file format. Also, we have integrations with various engine, Flink for streaming ingestion, Spark for batch processing, and StarRocks for OLAP queries, and also Iceberg for AI applications. And all of our data resides in a hybrid cloud, AWS, you all know, and to China cloud provider, Alibaba and Tencent. So it's the whole picture of Iceberg. When I joined RedNote 3 years ago, the first main use case is how to speed up the data ingestion. So the very beginning, either of our core data pipeline and of our Iceberg journey starts at the event log ingestion. Previously, our ingestion pipeline, it was in a batch manner. The log server log events as files and upload the files into the object storage in Tencent, and then just copied to AWS, which is registered as hourly partition half table, and then shuffle again to another half table, which is partitioned by the domain columns. The whole pipeline involves 2 copies of the data and introduce a latency up to 2 hours. And thanks to Iceberg, we evolved the pipeline to a near real-time manner. And the log server sends the events to Kafka, and we consume the Kafka source and shuffle by the domain partition columns directly in the Flink jobs, and then flush them to the Iceberg tables in AWS. So whole pipeline reduced the data latency into 5 minutes, and it is impressive work. So one of the challenges in this pipeline is how to handle the streaming shuffle. At that time, 3 years ago, there were only 2 distribution modes in the Flink Iceberg Sync. Neither of them were working well in our scenario. I will briefly introduce the 2 distribution mode. The first is the forward mode. The source operator would directly forward the event into the downstream file writer, and each file writer would create a Parquet writer for each partition. So that would cause 2 problems. One is the high risk of out-of-memory exceptions, since every Parquet writer would buffer row group data in the memory, and by default is 128 megabytes. And the second problem is it will create too many small files. This is the first distribution mode. And the other distribution mode is key by. That means the event is hashed by the L partition columns, which obviously could cause the data skew problem and further back pressure the whole Flink job. So we got to introduce our own custom Flink partition. The idea behind it is quite simple. If we could collect the statics on the source operator and using the BIMPAG algorithm to generate a shuffle strategy, which is to achieve a balance between the more even traffic and a few fanout-writers, which means a few data files. Yeah, as the picture shows, the green part is shuffled into fanout-writer 1, and the other part is shuffled to fanout-writer 2 with even traffic and fused fanout-writer. And another question here is how to dynamically collect the statics, because the traffic varies as the time goes. How we solve it is to align the collection into the Flink exactly once mechanism. First of all, we use the Flink Global Aggregation Manager for the coordinator role. So when on the process phase, every operator would keep the local map states, a partition level status, and updating the statistics using window and sampling to reduce the collection overhead. Once the Flink trigger a checkpoint, the CM, the operator, would send their local map states to the global aggregation manager. And the global aggregation manager is responsible to merge all the map states on a specific checkpoint. Once all map states was merged, then the notify checkpoint complete is triggered. Then global aggregation manager would broadcast the merged map states to all the operator, and each one would refresh the bin pack strategy based on the aggregated states. So we can refresh the states with a latency of the checkpoint interval. By the way, as for the cold start problem, there was no states, and event with a new partition column partition comes. We use the default behavior is hash by, which would lead to a data skew problem and further back pressure the whole job. Frankly speaking, we don't have an elegant way to solve this problem. We just manually trigger a checkpoint when the job starts and process a little bunch of records. So we manually trigger the snapshot to get the map states. So that's all about the shuffle. Today, about 60% of our daily increased Iceberg data comes in a streaming way. So I have summarized some key practice we are trying to achieve a better throughput and stability of the Flink Iceberg sync. The first one is the shuffle, as discussed in the previously talk. And the good news is an elaborate range distribution mode is now available in the Flink Iceberg sync, and you don't need to write by yourself, just use it. And since all our data resides in the object storage, so another focus is on the S3 file I/O, upon which we have several practice. The first, S3 upstream would write staging files on local disk and then upload them to object storage in an async way. So we can staging files on SSD for a better I/O performance. And since Flink checkpoint would flush all the parquet writer and close them and upload the files, so it's better to set a smaller parquet row group size to avoid the S3 traffic breakout on the checkpoint. This tool was to optimize the throughput, and our data always exchange between hybrid cloud. So that means network issue often happened in our scenario. So we implement a retry policy on S3 outstream to avoid expensive Flink failover. Besides, we define the watermark in our Flink source and commit the watermark in the snapshot so that the downstream consumer could know when the data is ready and start the scheduling. Also, we create a table manager service which automatically create table actions like expire snapshot. And the last key practice actually is Flink is really expensive, both in resource and human maintenance, so adopt it in the key pipeline. And after the data is ingested into the lake, another big progress towards to the lakehouse architecture is leveraging the StarRocks Iceberg to speed up the OLAP queries. Comes to our OLAP architecture, there are 3 tiers. The first tier is the raw data lake tier. Ad hoc queries were performed on hundreds of petabytes raw data and within a latency of minutes level. The second tier is Clickhouse tier. Tens of petabytes data was loaded into Clickhouse, and we provide a 10-second level performance. And the third tier is the StarRocks tier. Only a small portion of golden data could be loaded into StarRocks, and it provides a sub-second level query performance. So one motivation behind this arc is that if we can perform a 10-second level query latency directly on the leg, we can actually eliminate the class tier, which is promising since it can save tens of petabytes storage. So after in the past years, we have some learnings from Clickhouse tier, and the biggest challenge actually is that the data loaded into Clickhouse actually are produced and consumed by different teams. The table model, primarily the sort key, is defined pretty well when the table is created, so the performance is good. But as the time goes, the query pattern varies, so the index miss would lead to poor performance. And in one of our production cluster, we observed that 70% of the query actually are doing the whole table scan. Yes, that was the big question. And the second drawback is Clickhouse doesn't support shuffle join, which means our customer always to assemble several table into a big giant white table. This burden the ETL pipelines. The third drawback is data silos. We have duplicated data and the ETL maintenance headache. So we solve these 2 drawbacks via the StarRocks Iceberg solution. For the first, the biggest problem, we actually maintain an auto service to collect the telemetry, the query telemetry from StarRocks. And based on the telemetry, we automatically optimize the Iceberg clustering based on the order rewrite procedure to maintain the datascaping performance as the query pattern varies. That's the biggest benefits. So we don't care about the query. The consumer is changing their query patterns. And the second is join problem. The StarRocks original support shuffle join, which is impressive and fast. And the third one, since we directly perform the query on our external Iceberg tables, so we can animate the Clickhouse tier. Yeah, I don't need to ETL and load to the Clickhouse either. Then checking the query performance. The left side is a comparison of query profile on the same table with or without the order. We can observe that the scan bytes is reduced almost 90% after the order. And the left side was the performance benchmark between Clickhouse and our StarRocks Iceberg solution with or without cache. The figures are from one of our core cluster, and the figure indicates 3 times faster in performance, and that's impressive work. So last year, we have migrated one of our biggest Clickhouse cluster into the StarRocks Iceberg solution. And I have summarized some key practice during the migration. The first is we conclude the order strategies based on the production experience. Whether we to enable the order on a table, since the order means money, there are two basic conditions. One is the table should be frequently queried. And the second one is the average number of files per partition should be above 10. And the switch about which columns to choose to perform the order. We also have two conditions. One is we use the top 3 frequently filled columns, and the column NDV should about 15. Both the 10 and the 15 are based on our production, observation, and experience. So it's just a reference. And StarRocks can cache the data in both memory and disk. Is very critical in our case, since it's significant. It can reduce the remote call of our object storage, which can benefit for the performance, either the performance and the stability. The below chart shows the network traffic. When we turn on or turn off the data cache, it shows the net traffic reduced as 5 times. Another is the big query isolation is also very critical. Per the important business, we always deploy several StarRocks cluster, and one of which is dedicated for the big queries. We call the class the slow cluster, and we have deployed a gateway service to receive and estimate all the queries. Once one query was judged as a big query, and it will be routed to the slow cluster. That's all for the OLAP scenario. And recently work is for the AI applications. We we have built a sample lake based on Iceberg. First, let me briefly introduce the machine learning pipeline of our company. So when a feed request from client side, a multi-line ranking service is responsible to return a rank list of note. And behind the ranking service, there were a lot of online models. Each models would infer a score based on the context and the feature store. This blue box are the online offlines, while the yellow box are the offline pipelines. The key component in the offline pipelines is a sample, which actually is a table of joint records of label and features. And the sample is fed to the offline training process to generate a new model or to generate the incremental changes on the online models and then deploy them to the online to refresh the online models. That's the whole picture of our machine learning pipeline. And based on these pictures, one of our algo engineer daily job is to do the offline feature investigation, ultimately to optimize the online model. So the ideal way to do this is check out a test branch based on the main branch of the sample and join with the test features to generate a joint sample, which will be fed to the offline training and generate a new model. Then the new model will be evaluate in while A/B test. If the result of evaluation is nice, then we can deploy the features and deploy the model. So this is the engineer's POV point of view. But how we can facilitate the invest pipeline via Iceberg? As a sample table is always with thousands of columns and up to petabytes storage. So on the traditional or previously copy on write process, it will need to read all the columns, add a new column, and then write all the columns back, which means massive I/O cost. So we extend the Iceberg V1 spec internally by adding a new data type, a new data file type, which physically consists of a base file and a bunch of update file. So we can process the adding column or the partial update in a merge on read path, which significantly reduce the I/O bytes up to 80% in our case. And this is the core feature. And besides this, we can use leveraging the Iceberg branch mechanism for easily manage all the investigation process, since many investigation is concurrently working on a sample. At the last, we have extended the compaction procedures to two types. One is major compaction and another is minor compaction, and is easily understood. The minor compaction is responsible to merge several update files to a compact update file, which is less I/O intensive. And the major compaction is responsible for coverage the base file and the update file, and then merge them to a base file. So that's the key features. And this slide shows how we using the Spark merging to grammar to do the partial update, merge into the target table using source dismiss feature on the primary key, and when matched, then update the update columns. The underlying implementation is based on the MOR reader on V2 format. We did a little bit of change on that, and the whole steps are following as this picture. First step, we could only read the join key, update column, and three meta data column files, position, and partition. And we use the left join to the best the best file as the future source to generate a row matched update file. Set the unneeded column to null. That means the original feature columns in the base sample. And we repartition the dataset by partition and the file, and sort by the partition file position. So we can align the base file and the update file by file, and the record line by line. This means the small unit of plane is actually based on the file level rather than the row group level. After the sort, we can write the update columns in the update files and then commit them as the overwrite operation. Yeah, that's all for my talk. Thanks for your time.
Great. Thank you so much, Simon. At this given time, if anybody has any questions, we strongly urge you guys to put it in the Ask the Speaker tab on the right-hand side. We'll give it about 30 seconds or so. If any questions do come in, I'll read them out to you here, Simon. Okay, it seems like it's pretty quiet. All right, so with that, I just want to go ahead and say thank you so much, Simon, for joining us. And as a reminder, all of these sessions will be available on demand within about an hour after this event's over. And up next, we have efficiently managing table with thousands of columns using Iceberg with Tencent, Mr. Liu. So that's going to be coming up next. We all hope to see you there. And with that, Simon, thank you so much for joining us, and have a great show, everyone.
Thank you.
Bye-bye.